given by Professor Cenke Xu. It's titled TXA, Field Theory, Description, and Classification of Almost Topological State, Part 3.
Okay, so we will continue what we left yesterday. So today I will talk about, yesterday everything I talked about was within the new cohomology formally that Xiaogang discussed in his talks. Today I'm going to go beyond that. I'm going to discuss things that is beyond the cohomology. But again, I will not use those math. I will just simply use a field theory to describe those states beyond the group cohomology. Okay, since everything I'm going to talk about today actually is related to the concept called anomaly. So I will first try to review anomaly and SPD state, the relation between anomaly and SPD state. So here is precisely what I mean by this relation. Suppose I consider a d-dimensional SPD state with a d-1 dimensional boundary. And suppose this d-dimensional SPD state has a global symmetry G, and this global symmetry G is defined on the lattice. It's a lattice symmetry, defined on lattice symmetry. Then its boundary cannot exist by itself. If I only take one boundary, the boundary theory must be anomalous, which means that there must be another mirror sector on the other boundary, on the opposite boundary, cancel out the anomaly. Cancel out the anomaly. So one example is that the 3D chiral fermion, by 3D I mean 3 plus 1D, a 3 plus 1 dimensional chiral fermion with precise global U1 symmetry cannot exist alone in 3 dimensions. Okay? It must be a boundary of a 4-dimensional system. And we know what the 4-dimensional system is. The 4-dimensional system comes better. It's a 4-dimensional fermionic SPD state with U1 symmetry. It's the 4D integer quantum Hall state. Okay, this was first discovered by Zhang and Hu, although they didn't really worry about anomaly, but that is the first model whose boundary gives such a 3 plus 1 dimensional chiral fermion with a global symmetry. Yeah, okay. So,
is it the same as the no-go theorem? You must have two even number of fermions.
Yeah, I will get there. Yeah. Okay. So yeah. So how do we see the anomaly? So if the global symmetry G can be gauged, which means that if I can couple the system to a gauge group, which enhance the global symmetry G to a gauge symmetry, then this d-1 dimensional boundary field theory must have gauge anomaly. Okay, this is one way to do that. But it's not general enough because there's some symmetry that we don't really know how to gauge. The time inversal symmetry, I mean, we don't know how to gauge that. But for those symmetries that we can gauge, then if I only gauge one of the two boundaries, then this theory must have anomaly. For example, the 3-dimensional chiral fermion will have a U1 gauge anomaly once this global U1 symmetry is gauged. Okay, there's a famous no-go theorem proved by these people, and they claim that on the lattice there cannot be a chiral fermion, single chiral fermion. And by lattice they mean 3 plus 1 dimensional lattice. And it's not extra dimensional, 3 plus 1 dimensional space-time lattice. There cannot be a single neutrino or a single chiral fermion. But they made a very strong assumption here. They assume exact conservation of the particle charge even at the scale where the lattice quantum is relevant. It means that they assume a U1 global symmetry for the chiral fermion from infrared to the cutoff, to the UV cutoff. They always assume the U1 symmetry. It's always there. Okay. So this gives us the room. This gives us room to cheat. Okay. Suppose I want to get a 3 plus 1 dimensional chiral fermion in a 3 plus 1 dimensional system. For example, if I infinite matter, suppose I want to realize a 3 plus 1 dimensional chiral fermion, which looks like a chiral fermion, on a 3-dimensional lattice. So what I can do is that I can just break the U1 symmetry on a lattice scale, violate their assumption. Okay, break the U1 symmetry on the lattice scale, and I guarantee that the U1 symmetry breaking term is irrelevant. Okay, it's irrelevant. If I guarantee that, then at low energy, I will not see the U1 symmetry breaking effect at all. Okay, I will not see that. But I go to UV, I will see the U1 symmetry breaking, then it violates the no-go theorem assumption. Okay, but nevertheless, because I can make the U1 symmetry breaking term irrelevant, then at low energy, this theory may still just look like a single chiral fermion. Let's look at a single chiral fermion. Okay, this is doable. It's doable. Okay, so I'm going to get back to this point later, but now let me look at another kind of anomaly, which is also something that Xiaogang mentioned yesterday. So Xiaogang introduced the concept of invertible topological order. So this kind of topological order has no symmetry at all. It has no symmetry at all. That means that its boundary states is gapless, but its boundary states has no global symmetry that we can gauge. It has no internal global symmetry we can gauge. Then in this case, the boundary still must be anomalous, right? Because the boundary has to be anomalous. Otherwise, it can be itself existence, but it doesn't have to be a boundary. Then the only anomaly the boundary of ITO can have is the gravitational anomaly. Okay, that's the only anomaly it can have, the gravitational anomaly. Okay, so let me give you one example. So let me talk about the incandescent matter is well known. So the classification is already well known. It's a topological superconductor with no symmetry at all. Okay, there's a class of topological superconductor without assuming any symmetry at all. Okay, so this classification is this. It's worked out by two different groups of people, and the classification is here. Okay, so in 1D, the Z2 classification, 2D Z classification. 2D, this Z classification is actually the same as the integer quantum Hall Z classification. This Z basically corresponds to, all the field in different Landau levels. Okay, integer quantum Hall state has a U1 symmetry, but we can break that U1 symmetry completely. Okay, the state will still remain non-trivial. The reason integer quantum Hall in 2 dimensions is stable against the U1 symmetry breaking is precisely because its boundary, which is a chiral fermion in 1 dimension, besides having U1 anomaly, also has gravitational anomaly. So integer quantum Hall state, its boundary is protected by gravitational anomaly, not just protected by U1 global anomaly. Okay, that's the claim. So we're going to go to higher and higher dimension. We know that actually in incandescent matter, we all know that in 4 dimensions, I just told you, in 4+1 dimensions, there is an integer quantum Hall state worked out by Shoucheng Zhang and Jiangting Hu. Okay, in 4+1 dimension, there's an integer quantum Hall state. However, in 4+1 dimension, it's an integer quantum Hall state absolutely need U1 symmetry. That's a very big difference between the 2-dimensional integer quantum Hall and 4-dimensional integer quantum Hall. So 2D integer quantum Hall does not need any symmetry because its boundary has gravitational anomaly and U1 global anomaly. Okay, but a 4-dimensional integer quantum Hall, its boundary is a 3+1 dimensional chiral fermion. But a 3+1 dimensional chiral fermion only has a U1 gauge anomaly. It does not have any gravitational anomaly. So this means that if I break the U1 symmetry, the 4D quantum Hall will be trivial, but a 2D quantum Hall will not be trivial. Okay. So the same situation happens again in higher dimension. For example, in 6 dimension, the integer quantum Hall in 6 dimension again does not need any symmetry anymore. It does not need any symmetry because it's a boundary with 5+1 dimensional matter. 5+1 dimensional chiral fermion again has a gravitational anomaly. Okay, so just go to periodic. And then have Z2 here, which means that a single copy of integer quantum Hall here actually will be stable, 2 copies will be unstable. Will kind of unstable. So this is the.
So I remember in their classification scheme, actually the dimension 9, it start from dimension 9, the pattern is
yeah, it happens again. Yes, Z2, and Z.
I just want to make sure I understand correctly. So I remember they only bring like dimension 1 to 8 and the others just repeat.
Yeah. It's indeed repeating.
Yeah, okay.
It's repeating. Yeah.
But this 2Z, that's something extra?
I don't think so.
Only 1Z.
Yeah. I don't know what 2Z is. It's no, I don't think there's anything extra. It's just all free fermion.
But what I try to say is that in the sense their table is not that complete. Sometimes when they say Z, it could be 2D, 3D, 4D.
Yeah.
There's they're saying that some unitary symmetry doesn't count, but sometimes that's
let's ignore this true rule right now. Okay? I mean, so this z correspond to 6-dimensional integral. That's good. Okay, so turns out that this table was actually also worked out by Wheaton long time ago. Although Wheaton was talking about something totally different. He was talking about gravitational anomaly of single Majorana fermion. By single Majorana fermion, I mean that it's the smallest Majorana fermion. The smallest Majorana fermion cannot be reduced anymore. For example, in 1 dimension, 1 + 1 dimension, he was talking about a wild Majorana fermion. It's one single Majorana fermion, but only moved to the right side. Wild Majorana fermion. And he was calculating the gravitational anomaly. Then he showed that in the 1 + 1 dimensional Majorana fermion, which is the boundary of a 2-dimensional p-type topological superconductor, this guy has a perturbative gravitational anomaly. And 2 and 3 has no anomaly. And 4 also have no anomaly. But in the 5 + 1 dimensional Majorana fermion, again, has a perturbative gravitational anomaly, which corresponds to the Z classification in 6 dimension. Okay, the bound state. And in 7 and 8, Majorana fermion has a global gravitational anomaly. I will explain what it means later, but this corresponds to Z2 and Z2 here. Okay, and dimension 9 also perturbative corresponds to Z here. This table also repeats itself. Okay, every 8 dimensions will repeat itself. So we can see that actually gravitational anomaly and the classification of topological superconductor with no symmetry at all, they are completely consistent. Okay, they're completely consistent.
What about the 0 dimension corresponding to the top?
Yeah, that's also G. That's also G here corresponding. That's also G. So global. Yeah. Okay. So these two tables actually are completely consistent with each other. Okay. So this means that it's really true that we can use a gravitational anomaly to classify fermionic or even bosonic short-range entangled state. Okay, this is the one specific example, and this example is very simple because of free fermion. Okay, it's free fermion. So all these classifications come from classifying all the gamma matrices. If you play with all the gamma matrices, you will see the result come out immediately. Okay, but has a very deep reason, which is the gravitational anomaly. Okay, but I haven't shown you what a gravitational anomaly look like. Okay, what is gravitational anomaly? So gravitational anomaly is this. In general relativity, we can do a general coordinate transformation like this. Okay, and eta and x go to x plus eta, and eta can be any function of the local coordinates. Okay, so suppose the system has no gravitational anomaly, then this system will be general coordinate invariance, okay, after coupled to a gravitational field. However, suppose system has gravitational anomaly, the system will no longer be invariant under the general coordinate transformation. So you will get something like this. To be more precisely, the energy momentum tensor will no longer be conserved. Okay, once the system has a gravitational anomaly. So you see some equation like this in 1 + 1 dimension. And in 2 + 1 dimension, this derivative of energy momentum tensor will have 2 terms. Okay, 2 terms, different kind of tracing between all the curvature matrices. Okay, different tracing with different curvatures. And if I go to higher and higher dimension, there are more and more terms that will appear because there are more and more different ways to take trace of all the index of the curvature tensor. Okay. So this is a perturbative gravitational anomaly. Okay. So what is the global gravitational anomaly? Global gravitational anomaly simply means that the partition function of that Majorana fermion will change sign under certain large coordinate transformation. It will change sign. It's the same as a well-known SU2 Wheaton's anomaly. Okay. So in SU2 Wheaton's anomaly, if I do a large SU gauge transformation, the partition function of the chiral fermion will change sign. Same thing happened here. Okay. In the 7 dimension, 8 dimension, actually, if I do a large global coordinate transformation, it's going to make the partition function change sign. Okay.
So what is large coordinate?
Topologically non-trivial.
Oh.
Large means it's a transformation called topological. Okay, so this is what gravitational anomaly means.
So how do you relate these two ideas? I'm not familiar with the upper one, but how do you relate these two?
These two?
Yeah.
Yeah, normally a global anomaly can be viewed as a perturbative anomaly reduced from a higher dimension. But here I'm not sure how to do that actually. I admit here I don't know how to explicitly do that. Yeah, here I don't know how to do that, but usually that's the case. Okay. Yeah, okay. So in the free fermion case, so I showed you the classification of free fermion SPT, free fermion topological superconductor without any symmetry. And I showed you that their boundary has a very, is precisely consistent with the gravitational anomaly. And in the free fermion case, these states are very easy to construct. I said the two-dimensional integer quantum Hall state and P-IP topological superconductor, which is just a half of the integer quantum Hall state. It has a chiral fermion on its 1D boundary, so it does not need any symmetry to protect stability. Okay, I can break any symmetry I want. There's no backscattering, and the reason is that it has a gravitational anomaly. And then we can think of a bosonic analog. So is there any boson system which behave like a two-dimensional integer quantum Hall? This means that can I find a two-dimensional boson system which does not need any symmetry, and the bulk is completely trivial and non-generate, but the boundary is gapless without assuming any symmetry. Okay. This statement is equivalent to say that can I find a 2D bosonic state with a trivial bulk spectrum and also with a gravitational anomaly as the boundary. Okay, is that clear? These two statements are the same. Okay, if I want to find a system without any symmetry but the boundary is gapless, it means that I need to find a system with gravitational anomaly as the boundary, because I break all the symmetry. Okay, so it turns out that in the boson system there is one state like that. This state is described by a 2+1 dimensional transition theory. Okay, this kind of transition theory with a K matrix, and the K matrix has to take a certain specific form to make sure all these happens. For example, has to make sure that all the diagonal components are all even to make sure that this system is a boson system. It does not have any Fermion statistics or fractional statistics. Also has to satisfy that the determinant of K must be 1 to make sure the bulk has no topological degeneracy. And the third has to satisfy condition to make sure the boundary is a chiral, the boundary has a gravitational anomaly. Okay, so it can be gapless boundary. So this is the famous two-dimensional E8 state. Okay, so these are all well known. Okay, so now the question is that can we find higher dimensional analog? Okay, can we find a higher dimensional analog of a two-dimensional E8 state? Okay, so first let me say that this E8 state itself is already beyond the group cohomology Xiaogang introduced in his first two lectures. The reason is very simple, because the group cohomology is to calculate some property of a group. Right? If I don't have any symmetry, the group is trivial. If you calculate anything for a trivial group, you get a trivial answer. Okay? So this state itself is already beyond group cohomology. Now let's try to find, can we find a higher dimensional analog of this state? Okay? Of course, it's very easy to find a higher dimensional analog of an integer quantum Hall state. I said the two-dimensional integer quantum Hall, 6 dimension, 10 dimension, every 4-dimensional integer quantum Hall, they behave the same way. Their boundary always have gravitational anomaly, so boundary is always stable. Okay. But then here, I want to do boson state, and this means that so the question becomes, can we find higher dimensional boundary bosonic theories which are gapless without assuming any symmetry? Okay, can we find a higher dimensional boson systems, without any symmetry? It must be gapless, and this theory will be the boundary of the bulk theory I want to study. Or can we find a higher dimensional boundary topological theory with gravitational anomaly? Okay, also, so all these statements are the same. Okay, all these statements are the same. Okay, so it turns out that Wheaton already answered a part of the question for us. Turns out Wheaton calculated the gravitational anomaly not just for Dirac fermion. He had to calculate gravitational anomaly for some boson system as well. So Wheaton demonstrated that in all 4K plus 2 dimensional space-time, which is the 4K plus 1 dimensional space, the self-dual rank 2K tensor boson field theta will have gravitational anomaly. Okay, so in 4K plus 2 dimensional space-time, we define a theta, which is a 2K form antisymmetric tensor field. And suppose theta satisfies this condition, which is the d theta equals to a whole star d theta satisfies this condition, we call it self-dual condition, then this theta field will have gravitational anomaly. Okay, will have gravitational anomaly. This is something Wheaton calculated. Okay.
I think this one, Chris was elaborate.
Sorry?
This also Chris was.
Oh, okay, yeah.
String theory.
Yeah, pretty sure that is. Yeah. In string theory, this field also shows up. Okay, anyway, so if I take k equals to 0, which means that I consider a 2-dimensional space-time or 1 plus 1-dimensional space-time, then this condition precisely reduces to the chiral boson condition. Okay, precisely to the chiral boson condition. So it means that this is indeed a higher dimensional generalization of the chiral boson. Higher dimensional chiral boson. Okay. So now we need to find a bulk theory for this theory. Okay, this is a boundary theory. So we need to find a bulk theory for this theory. We know that the bulk theory for a 1 plus 1-dimensional chiral boson is a 2 plus 1-dimensional Chern-Simons field theory. Then actually after a few lines of algebra, you can show that the bulk theory for this theory is this Chern-Simons theory. It's a higher dimensional Chern-Simons, but now this gauge field C will be a higher rank gauge field. It will be a 2k plus 1 form antisymmetry gauge field. Okay, this is the Chern-Simons gauge theory, whose boundary will be this self-dual. And as the boundary, C equals to d theta. Okay, that's the relation. Okay. Which means that we have a candidate bulk theory, which gives me the boundary boson theory, which must have gravitational anomaly, which means that it must be gapless. And I so far haven't assumed any symmetry yet. Okay, everything, so I didn't assume any symmetry. So, yeah. Okay.
But in this generalization, do you just get this unique term, or you could get other?
Oh, I mean, the K must have some conditions. And with those conditions, I only find one matrix. Yeah, again, the K must satisfy some condition to make sure that this bulk state is some state I want. Okay, I want to look for a boson state whose bulk is trivial, is boundary non-trivial, and is a boson state. So this means that first of all, determinant of K must be 1, otherwise system will have a topological degeneracy in the bulk. And actually, when we talk about a higher dimension, the topological degeneracy will be huge. It will be huge, very, very big topological degeneracy. So we want to make sure determinant K equals 1. And also we want to make sure the system, the boson system, means that I want to make sure that all the excitations of the system must be bosons. Okay? So what kind of excitation do we have in the system? Because C is a 2k plus 1 form gauge field. It couples to a 2k plus 1 form matter current. So this 2k plus 1 form matter current will correspond to 2k dimensional matter. Okay, so matter. Okay, this is the only thing we can say. So we must say that this theory describes a membrane theory. It's matter field and membranes. Okay. But the calculation for statistics is still the same thing. We can still calculate the braiding statistics between membranes. And it turns out that all the diagonal term has to be even to make sure the membranes are boson. Now here I want to say something that, in higher dimension, we cannot talk about braiding statistics between point particles. Okay, we can talk about braiding between point and particle in 2 dimensions. I can take one particle, and do this. It's a braiding. But in 3 dimensions, the braiding loop can shrink to 0. For 3 dimensions, I cannot talk about braiding between point and particles. But in 3D, I can talk about braiding between a point and a loop. I can do this. Okay. So it turns out if I go to higher and higher dimension, you can always talk about braiding statistics between membranes with appropriate dimensions. Okay, you can do that. So here, in this dimension, in 4k plus 2 space, we can talk about a well-defined braiding process for 2k dimensional membranes. Yeah. Okay. So it turns out that the same K matrix I showed you before, the same K matrix for the EA state will satisfy all the conditions, which means that this theory with this K matrix is the higher dimensional bosonic short-range entangled state without any symmetry that I'm looking for. Okay, this is state. Okay. Okay. So okay, so before I move on, let's discuss the simplest case where k equals 1. Okay, I said that when k equals that very, very big matrix, this system corresponds to some bosonic short-range entangled state. Now what if I just take k equals 1? Okay, what if I just take k equals 1? Okay. In 2 plus 1 dimension transaminase, if I take k equals 1, this theory is precisely integer quantum Hall state with nu equals 1. Okay, it's very easy. So now we can ask this question: if I for example in 6 plus 1 dimension, okay, when k equals 1 in 6 dimension, if I take k equals 1 here, so does this state correspond to 6-dimensional integer quantum Hall state or not? Okay, it's a very natural question to ask. Okay. Is this the same as integer quantum Hall state in 6 dimension? Turns out the answer is no. Okay, the answer is no. The reason is that okay, so this theory has a boundary gravitational norm which look like this. And the integer quantum Hall state's boundary is a 5 plus 1 dimensional chiral fermion. It also has some gravitational norm which also looks like this. However, they have different coefficient alpha and beta, and they are linearly independent from each other. Okay, they are linearly independent from each other. This means that this system and the fermionic integer quantum Hall state, they have different anomaly as the boundary. Okay, this
Are they
means.
related by some total derivative?
Sorry.
Are they related by some total derivative? There is a possibility you have a topological invariant in this dimension, which are also in terms of the curvature tensor.
Yeah.
Then they may be related. In that term, it's just a total derivative.
These two.
I'm not so sure. Suppose in this case we have more combination, and some of them are.
No, in 6 dimensions, these are all combinations. I think so only these two terms.
It can also allow the rich tensor, for example.
It doesn't show up in the calculation. Yeah, I mean, in written calculation, he only got these two terms. Yeah, he didn't get other terms. These are only two terms he had.
Here in the quotation.
Yeah. It only these only terms appear in gravitation. Okay, and the free, the free wild form and free chiral form in 6 dimension, and the boundary of this state, they have different coefficient and linearly independent from each other. So they have different anomaly. This means that they are really different bulk state. They are really different bulk state. These two states cannot be connected without a bulk phase transition. Okay. So it means that this state with k equals 1 is a very special state. It's not an integer quantum Hall state at all. Okay, something very special. I don't know what name I should give it, but it's not the same fermion state we see before. Okay. Another natural question we can ask is this. Okay. So in 6 dimension, we have this state described with this transaminase theory. So, but if I compactify 4 of the dimensions, okay, compactify 4 of the dimensions, and leave the 2 dimensions extended, then now what kind of a 2-dimensional state do I get after this dimensional reduction? Okay, is that clear? For example, I just make the 4th dimension into a torus or sphere or whatever you want to imagine. So in the remaining 2 extended dimension, what kind of state do I get? Okay, the naive guess would be that okay, then I need to go to 2-dimensional EH state, right? Or for example, if I take the theory with k equals 1, if I take theory with k equals 1, if I compactify 4 dimensions, then naively I would get a 2-dimensional integer quantum Hall state. Okay, that's the guess. But turns out the situation is a lot more subtle than this. It's a lot more subtle than this. So it turns out that whether we get a 2-dimensional short-range entangled state or not, or whether we get a 2-dimensional invertible top order or not, highly depends on the topology of the 4 manifold I compactify on. Okay, if I compactify this theory on 4-dimensional sphere or 4-dimensional torus, I will not get any non-trivial invertible top order in 2 dimension. However, if I compactify in CP2, it's some manifold with a strain topology. If I compactify on CP2, then the reduced 2-dimensional theory becomes 3 copies of 2D EA state. Only get 3 copies. The same thing happens for the k equals 1. So if I take k equals 1 here, if I reduce the k equals 1 theory on a 4-dimensional manifold and make the 4-dimensional manifold